Good morning, everyone. We'll be starting class in 1 to 2 minutes time. Yeah, I'm okay. It's just a little bit of acid reflux I have this morning. It just affects my throat a little bit. But after like half an hour time, it'll just recede and I'll be okay. It also doesn't help that we also have increased Sahara dust presence. So anyone who's got allergy problems, they're going to be affected over the next week. Alright, good morning everyone, and today's lecture is going to be based on the DFT, also known as the Discrete Fourier Transform. And we're going to be watching this in particular, how from our lectures last week, when we stopped at the Discrete Time Fourier Transform, the DTFT, how we move from the DTFT to the DFT in particular in today's lecture. And the DFT basically forms the basis of our transformation technique for taking a discrete time signal and getting its equivalent discrete frequency representation. In particular, even though that we're going to be watching the technique used for the DFT in the lectures that we're going to be doing on Wednesday, we're going to be looking at a little more of an optimized version of the DFT, which is known as the FFT, or more commonly referred to as the fast Fourier transform. And that's going to be the basis of technique that we're going to be using for our questions in particular. So try your best not to miss Wednesday's lecture when we start doing the FFT, because that's going to be a little bit important. But for now, today's lecture is going to show us the basis of the DFT that forms basically the entire base of our transformation technique. Alright, so let's get started. So we just need to do a little quick recap of what we've been doing for the last few lectures. We recapped where we had our Fourier series here, given by this x of t equation with the summation, and then we were able to transform this Fourier series into the Fourier transform, both of these here being continuous time versions, by applying these 5 limits here to the Fourier series in order to obtain the continuous time Fourier transform, also referred to as the CTFT. We also saw that we could evolve the CTFT here by doing a little more mathematical substitutions and so forth into what we refer to as our DTFT, given by these equations here, by the x omega and the x of t as of such. And even so that we see these here being our discrete time Fourier transform, these also still give us somewhat of a continuous time representation because we still have continuous integrals here. So this is going to bring us to the first point today, that even though that when we get our DTFT here, we did all these substitutions where we replaced t with nt of s, and it was possible to get the continuous x of t here being replaced by the discretized x of n into the DTFT and so forth. And even though we had the summation points, it was possible for us to formulate an inverse Fourier transform and an inverse discrete time Fourier transform. We saw in particular that the integral limits here went in between pi and pi, but this is still an integral, so this still gives us a continuous representation. The integral here, even though it goes between pi and pi, that means we still limit ourselves to every 2 pi, which is similar to where we saw the periodicity property for any discrete time signal that need to be periodic with a period of 2 pi in order for that property to be satisfied. But since we still have this integration here, that means it's still continuous in nature for the inverse, even though we have the discretized form here with the summation series as of such. So in general, what the DTFT will result in is in a continuous frequency spectrum, and you still need an infinite sequence x of n. And this isn't going to be applicable towards, because basically our x of n sequence could be finite. And if we have a finite sequence, that means the DTFT here isn't going to work as expected. So because of this continuous frequency spectrum, it also becomes impossible to represent this continuous frequency spectrum in digital hardware, because digital hardware is basically discretized forms. And that means the DTFT here is still not applicable to what we're trying to do here in DSP, because once we go into the digital realm, it's no longer a continuous signal that we're dealing with. We're going to be dealing with discretized signals. And like I said, it's impossible to represent a continuous signal in a discretized signal representation, because we always will have some sort of approximation error regarding this. So we'll get as close to it, but we'll never get a true full representation as required. So there are 2 procedures that you can use to transform the DTFT and make it applicable for our DSP course here and DSP in general. Sorry about that. So the first method is, instead of having an infinite sequence and an infinite summation, we limit that in the discrete time domain to some finite value capital N. So instead of having this infinite sequence here represented by our yellow shaded block, we now have a finite sequence here by applying our limits to finite values, or x of capital omega here for the DTFT. So this is the first way that we can go about doing this. So instead of using infinite sequences, we can now limit it to a finite sequence and apply our limits into the DTFT equation as of such. The second method is where we can actually sample the frequency domain capital omega, because remember, and using DTFT we were producing a continuous frequency spectrum. We need to sample that frequency domain and make it discretized in order for it to be applicable towards DSP, because like I said, our digital hardware only deals with discretized time signals or discretized frequency signals. Typically, in practice, you tend to use the same amount of samples that you took in the discretized time to represent the discretized frequency signal as of such. So you'll have equal spacing of samples regardless. And the equation for that equal spacing of samples is going to be given by delta omega here, and is equivalent to 2 pi on n. The reason why there's the 2 pi here, remember the discretized time signal and the discretized frequency signals are going to be periodic with a period of 2 pi. So as of such, this gives us the spacing in between two successive discretized points. If we want to know, like, okay, what's going to be the actual frequency per values here, we just say it's going to be 2 pi k divided by n, where k basically goes from 0 to 1 less than the total number of samples that you took. So at k equals 0, that represents our first frequency component. At k equals 1 will be our first at k equals 0, it represents the DC frequency component. At k equals 1, that will be our first frequency component. At k equals 2 will be our second frequency component, and so forth as we keep on going in our discretized frequency signal. So in doing this, that means now when we substitute in capital omega here equals to 2 pi k on n, and we place this into our general equation from the DTFT form that we have, we'll end up with this resultant equation here, giving us our discretized frequency representation that we were talked about in the previous slide. So since that output there is going to be a function of k, it's possible for us to truncate the entire DTFT by instead of having 2 pi k on n here, we just call this x of k, and we leave the right hand side of the equation as is to represent the k notation where we need to do our substitutions as of such regarding our DTFT equation. So this general form here where we sample the frequency domain, this is what we're going to be using, and this is what we refer to as our discrete Fourier transform of the discretized time signal x of n. Shorthand for this is just going to be DFT. And this here forms the basis of all our frequency transformation techniques for discretized time signals. Any other forms that you may see later on, meaning like the fast Fourier transform and any other optimized transforms, they take the basis from this equation and then figure out how to optimize it to make it a lot faster or a lot more efficient to do the calculations in particular. So this is the base for the Fourier transform regarding any discretized time signals. So what this basically means in layman's terms is that it will transform the discretized time signal being samples of the time domain in x represented as x events into the frequency domain as samples represented as x of k in general. Of course, if there's a discretized Fourier transform, the inverse discretized Fourier transform must exist to transform back from the discretized frequency signal into its equivalent discretized time signal. And its equation is given here in this blue shaded block. And in general, you can see here that the only difference that you have between the two is that now you're just going to have a 1 on n in front of the summation series there. The general equation just remains the same, and you just swap x of k and x of n on the left hand side or the right hand side of such the exponent here. The only difference with the exponent here is that this exponent here is to the negative power, and in the inverse discrete Fourier transform, this exponent here is to the positive power. So because these DFT and the IDFT basically uses summation points and summation series, it's possible us to actually program this in general, because each of these summation series here just represents a for loop. So this will be like for n equals 0 in increments of 1 up to n minus 1 here. And the same thing here for k equals 0, k in increments of 1 up to n minus 1. Same thing for the IDFT, and you just basically have two for loops where the first summation will be the outer for loop, and the inner summation here will be the next for loop that is indented inside that outer for loop. So you just have an outer for loop and an inner for loop if you're programming this in general. So that DFT and the IDFT that we just observed there is applicable to DSP because, like I said, DSP requires discrete signals in particular. You also make sure that the sequence lengths are finite in general. The shorthand notation that we use with the DFT is that we represent that exponent form that we saw as e minus j 2 pi divided by n as w of n. That allows us to shorten the writing of the DFT in particular. That w of n shorthand notation is what we refer to as a twiddle factor. And we're going to observe the effect of this twiddle factor in a little bit. So when we actually apply the DFT here to our x of n sequence, being common x of n, our discretized time sequence, and we have each one of these twiddle factors being multiplied by it because of the summation series here. So this will be for like w of 0 when n is equal to 0, w of 1, w of 2, w of 3, and so forth. And we keep on applying it throughout the entire summation series. What we see here is that the DTFT, we know that it's periodic with a period of 2 pi. And then the DFT here is now going to be a period of n, represented our samples because of the transforms that we just done. So any DFT spectrum is going to repeat after the total number of frequency samples that you had to begin with, because the DFT form was basically allowing you to sample the frequency spectrum as required. And the output frequencies here are given by this equation with the k index, which is just going to be 2 pi k on n that we just now saw. Our next way to represent this is just going to be k multiplied by the sampling frequency divided by n as well. And that sampling frequency is just similar to the 2 pi on n that we just saw there in particular. Each instance of these k frequencies, so this will be at k equals 0, k equals 1, 2, 3, and so forth. This is what we refer to as our bin frequencies. And the maximum frequency bin will occur halfway in the interval. Basically, it will be at k equals n on 2, or also when k is equal to half that of the sampling frequency. So if we watch a general idea of what the time domain signal would have been and then its frequency domain representation, we'll see here that, let's say it was going from 0, 1, 2, 3 up to n minus 1. When we transform this into the frequency domain, the discrete frequency domain using the DFT, you'll see here that 0 here will remain 0, but 1 here now becomes f of s divided by n, being the total number of samples. 2 here will be 2 f of s divided by n, so this 1 and 2 here and 3 and so forth will be the k index as required. And then the maximum frequency bin that we're going to be watching at is at f of s divided by 2, or half that of the sampling frequency. So let's say if n here was going up to 8, that means f of s divided by n here is where we have 7 f of s divided by n. This is similar to minus f of s on n because of this periodicity property that's going to be symmetric about f of s divided by 2. So just to illustrate what I'm talking about here, so let's say n here was equal to 8. So this will be at k equals 1, and this one here will be k equals 7. But because of the symmetry property about f of s divided by 2, that means here that k equals 1 is similar to that k equals 7 frequency component. So as of such, it's possible to say, okay, that f of s divided by n here is basically same as 7 f of s divided by n, but because it's going to be on the opposite side of f of s divided by 2, that's how we end up getting this just be equal minus f of s divided by n, just to satisfy that symmetric property that you observed earlier. So just note these frequency values here and the symmetry property that I just explained to you guys, because we're going to be coming back to this in a little bit. So if we go back to our DTFT example here that we did in our previous lecture, where we had 5 samples, which we know the periodic time here is going to be 0.2 seconds. And let's say instead of applying the DTFT, we're going to apply the DFT to this problem instead. So we need to figure out what's going to be the bin frequencies here. So we know our sampler time here is going to be T of S equals to 0.2 seconds. We also know that n here being the number of samples is going to be 5. So I'm going to write this in just for reference. So T of S was equal to 0.2 seconds, and capital N here was equal to 5 samples. So when we apply our equation here, being f of s equals to 1 divided by 0.2 equals to 5 Hz, this is basically just saying the same thing here as f of s here is equal to 1 divided by T of s to get our sampling frequency. And then the bin frequencies, because we know that basically they're going to be periodic about f of s divided by 2. So we can say here f of s divided by 2 is equal to 2.5 Hz. But we also know here that the bin frequencies also go such that they are k f of s divided by capital N, where k goes from 0, 1, all the way up to n minus 1. So what this translates to is that we're going to have, let's say, in our particular case, this is going to be 1 by 5 divided by 5. So we get 1 Hz. And then this is when k is equal to 1. And then if we had k equals 2, it would be 2 by 5 divided by 5. So we get 2 Hz and so forth. And then similarly, if we had k equals 0 here, that's going to be the same as 0 by 5 divided by 5 here, which gives us, oops, my bad. I'm going to rewrite this for you guys. So remember the bin frequencies here are just going to be k f of s divided by n. So in our case, is if k is equal to 0, that's just going to be 0 by 5 divided by 5 is 0 Hz. Then k equals 1, 1 by 5 divided by 5, which gives us 1 Hz, and so forth. And remember the maximum frequency here. The maximum frequency bin will be f of s divided by 2 with 2.5 Hz. And our T of s here was 0.2 seconds. Capital N here is equal to 5 samples. And this f of s equation here was basically 1 divided by T of s, which gives us all 5 Hz in particular. So that's how we obtain our bin frequencies here in particular, and how we obtain our f of s here as well, regarding these bin frequencies. And we also know where our maximum bin frequency is going to be stopping at, being at 2.5 Hz. The reason why we have integers here, because remember, on this k f of s divided by n equation representing each instance of our bin frequencies. And f of s and n just basically coincide because they're 5 and 5. So it's just going to be 0, 1, 2 up to the maximum bin frequency that we just have calculated here. So our x of n sequence here was basically 5 samples of just the value of 1, because each one of those magnitudes of each of those samples was just 1, as we just saw. And then our DFT equation is given by x of k here and the summation series. And we also know that the w of n, k of n factor here is equivalent to e to the minus j 2 pi k divided by n multiplied by common n here. It's possible for you to actually plug in this exponent form in MATLAB or Octave and it would actually calculate it out for you in general. But this is similar to us saying, let me write this form here. We're going to extrapolate this a little bit here. And we're going to say that theta equals to 2 pi k divided by n multiplied by n, and at w of n, k of n form, if we don't wish to write it in this complex exponent form, this is just basically to be cosine theta n minus j sine theta n. Let me write that a little bit neater. So that's if you wish to use it in its raw trigonometric form, but you can use it directly in its complex exponential form if you use a MATLAB or Octave, and it'll actually calculate out everything for you. Now remember, capital N here was the number of samples. K here was your index. And common N here is what you have to watch for in particular, which is also representing another index, which is going to be just basically our sample index in particular. So because this twiddle factor here is a function of k and n, we're going to have to figure out, okay, which one do we hold constant and which one do we modify in particular. And this goes back to, let me backtrack a little bit so you understand why we have k of n here. Let's go back a little bit because we just saw this when we're doing the programming part. This is basically because the reason why we have k and n here is because of these summation loops that we just now saw. So we have an outer summation loop, which is k equals 0, and inner summation loop, where n equals 0. So if we basically were doing the iterations here for that twiddle factor, the iterations will go such that it will be k equals 0, and then n will go 0 to 4. And then on the next iteration, it's going to be k equals 1, n equals 0 to 4, and so forth as we keep on going until we go k equals 4, n equals 0 to 4. And its general operation, because the inner loop here will proc regarding on any iteration of the outer loop here in particular. So that's how the twiddle factor basically works, because of that double summation series where the summations basically cascade into each other. So when you actually apply to the twiddle factors later on here, that means in general what happens is that we must be starting in such that it will be k equals to 0, and then n needs to go from 0 to 4. And then on the next iteration, it's going to be k equals 1, and then n needs to also go from 0 to 4 and keeps on going until we satisfy all conditions. So we can see here in particular when we have omega 5, 0, 4, this is when k is equal to 0 and n is equal to 4. And we can also watch here for this one. This is when k is equal to 0 and n is equal to 1, representing that summation notation that we just saw in particular. So in doing this, that means we have to calculate the twiddle factor values for each one of these x of k indexes here. So when k is equal to 0, that means we're going to have to, when k is equal to 0, we're going to have to calculate k equals 0, n equals 0, then k equals 0, n equals 1, k equals 0, n equals 2, and so forth, just for this x of 0 value here. So what happens is that k and n here will basically be taking the same values, but we'll be holding k constant for each one and then just modifying n to calculate the total factor values. So that means from W500 to W544, we're going to have to end up calculating 25 values for each one of those x of k's. And that means x of 0 will have 5 total factors, x of 1 will have 5 total factors, and so forth as we go into x of 4, having 5 total factors. So that's how we end up getting a total of 25 total factors that we have to calculate. Thankfully, I've calculated all this for you guys in general. So you actually can see all the total factors here represented by this nice table. And we just basically just substitute the total factors for each one of these as of such, and we can just calculate it out regardless. So if we calculate for x of 0 here, and calculate for x of 1, x of 2, x of 3, and x of 4, we basically see here that x of 0 here, being our DC component, is going to have a frequency magnitude of 5. But x of 1, 2, 3, and 4, which basically represents our first, second, third, and fourth harmonics, are going to have a value of 0. And the reason for this is that the nature of that DC signal is such that it's DC. There aren't any other sort of AC frequency components. So just from watching the general signal alone, once we know it's DC in nature and there weren't any kind of modifications of magnitude in it, we know that the only frequency component we're going to get is that x of 0 being our DC frequency component, and all other components, being the harmonics, are just going to be 0 in general. If we plot this, we basically see that in comparison to DTFT, which was a continuous spectra, and we got our nice shape of our graphs here, the DFT, because this is a discrete frequency spectra, means that we can only detect the bin frequencies and the magnitudes at those bin frequencies. We are not going to get this nice shape of the graph here. And I'm reiterating this. Remember, the DTFT produces a continuous frequency spectra, but the DFT here produces a discrete frequency spectra. So the DFT only gives us the bin frequencies and the magnitude at those bin frequencies. We do not get the shape of the frequency graph. If we superimpose onto it, we basically see that for each one of these bin frequency points, we have the same magnitude as the DTFT as of. So in commenting on it, the DFT, because it's a discrete frequency spectra of the DTFT, it basically approximates the DTFT. And if you don't have enough samples and bins, you're going to get a very poor approximation. So the more samples you have and the more bins you have, the better your approximation, but that also means that you need more memory to store these in particular. If we had an 8-sample DFT, and let's examine the computations involved here to see what's going to be the increase in accuracy. Remember, this being 8 samples, and if we apply to our DFT equation here, we're now going to have a lot of calculations to actually do here. Because that means k is going to go from 0 to 7, and n also is going to go from 0 to 7. And we have our our total factor here that we're going to have to try and calculate for. And that means that's going to be 8 by 8, which is 256 calculations for each one of those total factors, and that's quite a lot. So when we expand this out and we go from x0, x1, all the way down to x7, we can see in each case that's a lot of multiplications and additions that we need to do. So we have 8 multiplications to do per row, and then 7 additions per row, which is a lot of calculations to do for the DFT once we start going up in bigger numbers. And in general, this expansion is what we can observe for any endpoint DFT. So that means for any endpoint DFT, you're always going to have n squared multiplications, which was basically you multiply the 8 by 8. And then for each one of those multiplications that we just now did, we're going to have n multiplied by n minus 1 additions to do in order to formulate the frequency component. Just to give you a general idea, if we went up to 1024 points DFT, that's a lot of multiplications and computations that we have to do. And that's too much. It isn't practical for any real-time application because we're just going to be spending time doing calculations. So that's why there was a reason and a basis for finding a more optimized version of the DFT to speed up these calculations in general. And that's what's going to be forming our reason for using the FFT in Wednesday's lecture. So what we can do about this in general when we started doing the optimization process, we went back to the 12 factors in particular. Even though they were in the table form here, we can see here in some instances, there was some sort of repetition that was going on if we watch some certain diagonal values. So let's say if we watch the diagonal from here to here, you can see here that we just had some sign changes in particular. The real and imaginary components here basically were the same. The only thing that changed here was the sign in front of the imaginary component. Similarly, like if we watch this one here and this one here, we can see that these two values here are basically the same. But then if we watch for like this value here and this value here, they were basically the same as well. And then if we watch across this diagonal, you can see here that the only thing that changes is just the sign of the imaginary value associated with the 12 factor. So it's possible for us to discern some sort of pattern from the table in order to reduce the amount of calculation that we need to do. So let's observe the behavior when we have n here going in even values. So if we list out all the 12 factors here for W of 16, K, where K goes from 0 to 15, the first thing that we want to observe here is that we have a symmetry property where such that the first half of the 12 factors here are just going to be the negative counterparts of the second half. So W16 of 0 here, which was positive 1, just becomes negative 1. And then W16 of 1 here, which was 0.9239 minus this imaginary value. If we multiply by minus 1, we get minus 0.9239 here. And then the imaginary value here just transforms to a positive value. So there's a symmetry property that is observed in this 12 factor behavior. And for any values that exceed this K, so let's say if we had W16 of K, where K is equal to 16, it just flips over entirely because of the periodicity property of the DFT. So the symmetry property is given by this blue block here, which basically means that the first half of the 12 factor values here are equivalent to minus 1 multiplied by the second half of the 12 factor values. And the periodicity property means that if we go from, in this case, our listing goes from 0 to 15 for K. If K goes to 16, we just start back at the top of the table. So similarly, if K goes to 17, we'll now be at W16 of 1 and so forth. So the values just repeat themselves or cycle themselves. So that behavior allows us to, instead of doing all those calculations, we can now just do half of the calculations in general, which is a nice speed up because that means that's a 50% speed up. And the behavior of that 12 factor equation that we saw means that such that it's possible for us to actually keep on formulating even more optimizations as required. If we observe the behavior of this 12 factor here, for any one of these values that we get calculated, we basically see here that the magnitude of the 12 factor, when we actually perform some mathematical notations and so forth here, is that it will always be a magnitude of 1, which is referred to as the nth root of unity. And this phasor here, because of the direction given by this negative exponent, means that the phasor rotates clockwise instead of anti-clockwise. So if we plot out each one of these phasors here for this wk of n, we can see here that we have a nice 360-degree representation for our phasors and for our 12 factors. And the direction of rotation, because given by that minus complex exponential form, means instead of rotating anti-clockwise, we just rotate clockwise. So that means that when we add W8 of 0, we'll be at the 0 degree line here. And W8 of 1 is like at the minus 45 degree line here. Then W8 of 2 is at the minus 90 degree line, and so forth. So this actually gives us a nice indicator of how we can easily calculate out some of these 12 factor values, and then the only hard work that we need to do to calculate in between each one of these angles. Because in this graphical representation, W8 of 0 here, if we watch on the axis here, the y-axis here is imaginary and the x-axis here is real. So W8 of 0 here is just going to be 1. W8 of 2 here is going to be minus g. W8 of 4 here is just going to be negative 1. And W6 of 8 here is going to be positive g. And then anything in between, we can just calculate it out regardless, using our exponent form equation. Or we can just basically apply the angle values here and we can just get the same thing regardless, because we know that exponent form is basically cos theta minus j sine theta. So it's very easy to derive these values using this phasor representation and its graphical representation associated with it. So it's really easy at this point just to calculate these 12 factor values just using this form. And you'll realize that despite the number of samples that you have, they're going to coincide with the angles in particular. So you'll always have like you'll always have a 0 degree line here for Wn of 0. Then you'll always have a line where you're going to have the full factor here equals to minus j, then minus 1, and positive j regardless. So it's always going to help you speed up the calculation regardless. So when you try calculating the 12 factors here for n equal 8 and 16, you want to see that these cardinal points here representing north, south, east, west, they're always going to exist. So you're always going to know what those values are regardless. So in using the behavior of the 12 factors here, if we revisit the 8-point DFT, that means we only need to calculate for 4 points. And it's possible for us to recalculate that first example using the 8-point DFT and then just to plot the magnitude of x, okay, for that new DFT. So I want you guys to actually try this as practice. And you also have this nice optimized form of the 12 factors here. You don't need to do this via paper. You can actually try and program this in MATLAB or Octave to speed up the calculations for you. And just try this out and see basically if you can get the x0 value, because we know basically that signal is DC in nature, so anything else is just going to be 0. So x1, x2, x3, x4, all the way down to x7, we know that's just going to be 0. But just try calculating for the x0 value. And if you want to get a little more practice, try calculating for the x1 value. And the x0 value is just going to give you a DC value of 5, I believe. I think in this case it might be 8 because of the endpoints. And x1 is just going to be 0 regardless because of the nature of that DC signal. So try this for practice and let me know if you get those values in particular in the next lecture. So in calculating these DFT values, another way to speed it up is that it's possible to actually represent this by a matrix operation. So it's possible such that we can just have all the 12 factors here in one individual matrix, and then we can just multiply it by the x of k vector here to formulate our discretized representation capital X of k here regardless. And this is actually an example of parallel processing or block operations for speeding up our calculations even faster in performing the DFT. So a next thing to practice here is that see if you can actually formulate a matrix of these 12 factors using MATLAB or Octave, and then do the matrix operation here because it's just basically a matrix multiplication, and see if you can get the x0 and xk values here in particular. Just to summarize our DFT, and we watch our DFT pair in particular. If we watch the DTFT pair, this basically meant that we had an infinite number of time domain samples, and the frequency representation here was still continuous, resulting in our continuous frequency spectra. And formulating the DTFT into DFT, we basically truncated the number of time domain samples, and we were able to sample the frequency domain to formulate our x of k and our x of n representations for the DFT equation. All right, that basically brings us to the end of our DFT lecture. And in general, we just basically saw how did we move from the DTFT to the DFT and what was its actual practical applications. We also saw that in using the DFT, we were introduced to something referred to as the total factor, which is the W of n, K of n equation. We also saw that instead of doing the long complex exponential form, it's possible to represent this as a phasor graphical form to actually speed up and simplify the calculations and as such. We also saw that the total factors had a symmetry property and a periodicity property, which even allowed us to calculate for less total factors and to use these properties to calculate for the other halves required. And finally, we also saw that it's possible that in using MATLAB or Octave, we can speed up the DFT even faster by doing a parallel processing operation or a block operation in particular. So for practice, what I want you guys to do is just to do the 8-point DFT, and you can try and program this in MATLAB or Octave to see how you can go about doing it, as well as to do that same 8-point DFT using a matrix operation, which is going to be our parallel processing or block operation as required. And you're going to see that you're going to get the same values in particular. The reason why I'm telling you guys to do this in particular as well is because it's nice, good practice for you guys to get some real world application of how we can actually apply DSP techniques, as well as it also helps you verify your answers for any practice problems that you'll be getting in the problem sets or any drill questions or any exams in particular. So this is actually like a nice starting point for you guys to see, okay, how can we actually apply this programmatically, as well as it's going to be a nice verification tool to give you an idea if you're on the right step to getting towards the right answer. So are there any particular questions regarding the material delivered today for the DFT? Alright, it doesn't look like we have any questions. So if there are any questions when you guys are watching back this video for review purposes and so forth, feel free to leave them down in the comments below, or you can directly email me these questions in particular. Wednesday's lecture, remember I told you guys try your best not to miss this, because this is actually when we move on to the fast Fourier transform or the FFT, which is basically what we're going to be using throughout the entire course for actually doing our frequency domain representation of our discretized time signals. Oh, we have one question here. No, there's nothing else to note in particular. The course basically follows a somewhat similar structure of ECNG 2011 up to the FFT. And after that is that when we're going to have some new topics in particular. But the course is very straightforward. There aren't any kind of deviations or any sort of tricks that you have to worry about in particular. What you see in this course is what you get. So it's very straightforward regardless in this course. So yeah, on Wednesday's lecture, like I said, try your best not to miss this, because Wednesday's lecture is what we're going to be using for just an all frequency domain representation of any signals, and that also is a testable component in this course. So try your best not to miss that FFT lecture in particular. Also, Wednesday after the FFT lectures, we will be doing select problems from problem set 1. So if you didn't vote on my learning which 3 problems gave you the most problems while you're doing problem set 1, please remember to vote on my learning for those choices, because depending on the output of the voting results, that will determine which 3 questions will be done live in in Wednesday's session. Even so, after Wednesday's session, I will post up the solutions for problem set 1 afterwards, regardless. But if there's any questions that require some further explanation, I will do it live here on stream for you guys in particular. Alright, so until Wednesday, take care, be safe, and I will see you guys soon. Later.